Permutations with a restricted cycle structure. The following lemma turns the canonical cycle form into a very powerful tool. Lemma 6.15. Transition lemma: let P which maps from n-braces to n-braces be a permutation written in canonical cycle notation. Let G of P be the permutation obtained from P by omitting the parentheses and reading the entries as a permutation in the one-line notation. Then G is a bijection from the set Sn of all permutations on n-braces onto Sn. Example 6.16. Let P be our running example. That is, P is equals to 41253. Then G of P is equals to G of 41253, which is equals to 41253. Solution. It suffices to show that for each permutation, Q equals to Q1, Q2, Q3 until Qn written in the one-line notation, there exists exactly one permutation P in Sn so that Q is equals to G of P. In other words, we have to show that there is exactly one way to insert parentheses into the string Q equals to Q1, Q2, Q3 until Qn so that we get a permutation in canonical cycle form. To see this, note that Q1 certainly starts a new cycle, so the first left parenthesis has to be inserted to the front of the string. Where will this first cycle end? As we are looking for a permutation in canonical cycle form, Q1 has to be the largest of its cycle. Therefore, if I is the smallest index so that Q1 is less than Qi, then the first cycle has to end before Qi. On the other hand, if j is less than I, then the second cycle cannot start with Qj, as we know that Qj is less than Q1, and the cycles have to be in increasing order of their first elements. This implies that the second cycle has to start with Qi, and thus we have to insert the first right parenthesis and the second left parenthesis between Qi-1 and Qi. Then we can continue this deterministic procedure to find all our cycles. By an analogous argument, we have to start a new cycle at Qk if and only if Qk is larger than the leading entries of all previous cycles, which means in particular that Qk is larger than all entries on its left. As these entries are uniquely determined by Q, the preimage G inverse of Q exists and is unique. Example 6.17. The preimage of 4356,172 under G is 4356,172. The entries of Q that are larger than all entries on their left are called left to right maxima. Note that if Q has T left to right maxima, then G inverse of Q is equal to P has T cycles. Also note that the leftmost left to right maxima of Q is always Q1. Then the rightmost left to right maxima of Q is always the entry N. A surprising application of lemma 6.15 is the following. Proposition 6.18. Let I and j be two elements of n braces. Then I and j are in the same cycle in exactly half of all n permutations. Proof. As we can relabel our entries by switching n and I and switching n-1 and j, it is sufficient to prove that the entries n and n-1 are in the same cycle in exactly half of all n permutations. Let Q equals to Q1, Q2, Q3, and so on until Qn be an n permutation, and let G of P is equals to Q, where G is the bijection of lemma 6.15. As we said, the entry n of Q is always a left to right maximum, namely the rightmost left to right maximum of Q. Therefore, the last cycle of P starts with n, and the entries in that cycle of Q are precisely the entries on the right of n in Q. Therefore, B contains n and n-1 in the same cycle if and only if n-1 is on the right of n in Q, as that happens in half of all n permutations. The proof follows. The following surprising result shows that the likelihood that a given entry I is part of a K cycle is independent of K. In fact, it is 1 over n. Lemma 6.19. Let I is in n braces. Then for all k in n braces, there are exactly n-1 factorial permutations of length n in which the cycle containing I is of length k. Proof. Again, it is sufficient to prove the statement for I is equals to n. Then the general statement follows by relabeling. Let Q equals to Q1, Q2, Q3 until Qn be an n permutation. And let G of P is equals to Q, where G is the bijection of lemma 6.15, and let Qj is equals to n. Then the cycle C containing n in P is of length n minus j plus 1 as n itself starts the last cycle. So if we want C to have length k, we must have j equals to n plus 1 minus k. However, there are clearly n minus 1 factorial permutations of length n that contain n in a given position, and the proof follows. Theorem 6.9 tells us how to compute the number of permutations of a given type. Sometimes we do not exactly know the type of our permutations, but we at least know something about it. As it turns out, we can still enumerate the relevant permutations in many cases. In what follows, we will show a nice example for that. Other examples can be found in the exercises. Let odd of n, respectively even of n, be the set of n permutations with all cycle lengths odd, respectively even. Lemma 6.20. For all positive integers m, the equality, the size of odd of 2m is equals to the size of even of 2m holds. Proof. We construct a bijection phi from odd of 2m onto even of 2m. Let pi is in odd of 2m. Then pi consists of an even number 2k of odd cycles. Denote by C1, C2, C3 until C2k the cycles in canonical order. For all I, 1 is less than equals to I, which is less than equals to k. Take the last element of C2i minus 1 and put it to the end of C2i to get phi of pi, the image of pi. Example 6.21. If P is equals to 4, 5, 1, 3, 7, 2, 6, 8, then phi of P is equals to 5, 1, 3, 4, 7, 2, 8, 6. Note that if C2i minus 1 is a singleton, it disappears. Also note that the canonical form is maintained. We claim that phi is a bijection from odd of 2m onto even of 2m. Let rho is in even of 2m with the cycles C1, C2, C3 until CH. To prove that phi is a bijection, it suffices to show that we can recover the only permutation pi in odd of 2m for which phi of pi is equals to rho. While recovering pi, we must keep in mind that it might have more than h cycles because some of its singletons might have been absorbed by the cycles immediately after them. If the last value in CH is larger than the first value in CH-1, then create a singleton cycle with this value, placing it in front of CH, and repeat the whole procedure using CH2 and CH-1. Using CH-2 and CH-1. Otherwise, move this value from CH to the end of CH-1 and repeat the whole procedure using CH-3 and CH-2. If at any point only one cycle remains, create a singleton cycle with the last value in that cycle. It is then straightforward to check that the permutation pi obtained this way fulfills phi of pi is equal to rho. It also follows from the simple structure of phi that at no point of the recovering procedure could we have done anything else. Example 6.22. The pre-image of 41627583 under phi is 41267538. Example 6.23. The pre-image of 21536487 under phi is 1, 2, 5, 3, 4, 6, 7, 8. Now that we so nicely proved that the size of odd of 2m is equal to the size of even of 2m, we may well ask if there is a formula describing these numbers. The following theorem answers that question in the affirmative and has a touch of surprise in it. Would you have thought that the number of these permutations is always a perfect square? Theorem 6.24. For all positive integers m, the size of odd of 2m is equal to the size of even of 2m, which is equal to 1 squared times 3 squared times 5 squared and so on times 2m minus 1 squared. Solution. Because of a lemma 6.20, it suffices to prove the second equality. Let P be an m permutation with even cycles only. Clearly, we cannot have P of 1 equals to 1, as that would mean that the entry 1 forms a 1 cycle in P. So there are 2m minus 1 choices for P of 1. Then there are 2m minus 1 choices for P squared of 1, which is equal to P of 1, as we can choose everything but P of 1 itself. So far, we have chosen P of 1 and P of 1. These two elements will either form a 2 cycle when P of 1 is equal to 1, or they will not. In either case, we will have 2m minus 3 choices for the image of the next entry. That is, if 1 and P of 1 form a 2 cycle and I is an element outside that cycle, then we have 2m minus 1 choices for P of I. Indeed, we can choose anything except 1 P of 1. These have already been chosen, and P of I, as that would mean that I is a 1 cycle. If, on the other hand, 1 and P of 1 do not form a 2 cycle, then we choose the next element of their cycle, P cube of 1 next. The entry P cube of 1 cannot be P of 1 and P squared of 1, as those elements are already chosen and cannot be 1 either, as that would create a 3 cycle, 1 P of 1, P squared of 1. Thus, there are 2m minus 3 choices for the next element, in this case 2. Continuing this line of argument, we see that selecting our 2i minus 1st entry, we always have 2m minus 2i plus 1 choices. And selecting our 2ith entry, we always have 2m minus 2i plus 1 choices, as we can close cycles of even length, and the proof follows. Thus, we have a formula for the size of odd of n if n is even. If n is odd, then clearly the size of even of n is equal to 0, but we can still enumerate the size of odd of n. Theorem 6.25. For all positive integers m, the size of odd of 2n plus 1 is equal to 2n plus 1 times the size of odd of 2m, which is equal to 1 squared times 3 squared times 5 squared and so on times 2n minus 1 squared times 2n plus 1. Proof. We construct a bijection phi from odd of 2m times the braces of 2n plus 1 onto odd of 2n plus 1. In this bijection, we will need the notion of a gap position. This notion will be useful to solve some of the exercises too. And m permutation has m plus 1 gap positions, one before each element in each cycle, and one at the very end of the permutation after all entries. Example 6.26. The permutation 42513 has 6 gap positions, indicated by bars in the following array: 4 bar 2, 5 bar 1 bar 3. Let pi in odd of 2m and let k, which is less than or equal to 2m plus 1, be a positive integer. We define the phi of pi k as follows. First, take phi of pi, where phi is the bijection of lemma 6.20. Insert the new entry 2m plus 1 to the kth gap position of phi of pi. That will change one cycle to an odd cycle. Run the remaining cycles through phi inverse to get odd cycles. This way we obtain an 2m plus 1 permutation consisting of odd cycles only, and that permutation is our phi of pi. Lemma 6.27. The map phi defined above is a bijection from the set odd of 2m times 2m plus 1 braces onto the set odd of 2m plus 1. Proof. To find the reverse of phi, take pi prime in odd of 2m plus 1, put the cycle in pi prime, which contains 2m plus 1 aside, run what's left through phi to get even cycles. Read of k as the gap position in which 2m plus 1 is. Remove 2m plus 1 from its odd cycle and run all the obtained permutation, which has all even cycles, through phi to the inverse to get phi to the inverse of pi prime. Note that at every step we have reversed the corresponding step of phi. This completes the proof of the theorem.